Chapter 5.3 is diagonalization, and in this chapter is really kind of an extension of all the eigenvalue things we've been talking about, because it turns out that eigenvalues are the key to diagonalizing a matrix. First, what do we mean when we say we diagonalize a matrix? It means you take your matrix, whatever it is, and you write it as a matrix times a diagonal matrix times some other matrix, where this one is diagonal. What is a diagonal matrix? Well, that just means we have some matrix here. It could be anything we want. And then our diagonal matrix is a matrix that has numbers on the diagonal, but zeros everywhere else. So it's numbers on the diagonal, zeros everywhere else. And then you've got the inverse of whatever that first matrix is. So this is what it means to be diagonalizable and to have your matrix diagonalized. Why would we want to do this? Well, let's look at that real quick. So why would I want to diagonalize my matrix? The reason is because what would happen if you wanted to multiply by a matrix multiple times? And by the way, we've seen just with the Markov chain problem that multiplying by a matrix multiple times might be an important thing to do. Well, suppose I wanted to square a diagonalized matrix. If I wanted to square it, then what do I get? I get P D P inverse times P D P inverse. But what do you notice? You notice these two P's in the middle cancel each other out, and you end up getting P times that diagonal squared P inverse. And so what you can see is that it doesn't matter how many times you do it. If I had a third one, you would get those cancel out, and everything's going to cancel out. And so in general, everything is going to cancel out except for that first P matrix. And then you would just raise the diagonal to its power, and then you would have the inverse of that matrix. Inverse of the P matrix. Oop, I wrote the wrong one right there also. Okay. But this is a really nice result when it comes to diagonalizing things. And so, so what we can see, right, is that, and the nice thing is to raise a diagonal matrix to a power is pretty easy, because if your matrix is A, 0, 0, B, and you want to raise it to the n power, well, really you just end up raising the individual terms to the n power. And you can see why that should be, because if you multiply A00B times A00B, you get row times column. And the only ones that end up multiplying are the ones in the diagonal, and so they just end up squaring each other or cubing or whatever. So this means that raising A to a really big power is just the same as raising all those diagonal entries to a really big power, and then your matrix is done. So once a matrix is diagonalized, you have a lot, you're really capable of multiplying to really high powers. And like I said, when you think about Markov chains, you think about what's the long-term behavior. These diagonals will kind of tell you about the long-term. This equation will tell you about the long-term behavior. And also, there'll be some other things that we pick up furthermore about this. Well, okay, here is where I would do exercise 5.13 and do this with individual numbers, but I think you can kind of see how it's going to work. So I'm going to skip over 5.13. and just introduce you to the theorem. In an ideal world, I would try to really convince you why this theorem is true, and I will at a later moment, but for right now, I'm just going to tell it to you. So the theorem that we have is called the diagonalization theorem, and the diagonalization theorem just says that our matrix A is equal to a diagonal matrix, PDP inverse, where that P matrix is made up of the eigenvectors of your matrix, and D is made up of your eigenvalues. So in other words, when we end up doing this process, what do? We use our eigenvectors to create this matrix, and use our eigenvalues to create this matrix. And then then you get a diagonalized matrix, and everything works out just the way you would hope it works out. So that's our diagonalization theorem. But there's one important caveat, and that is it only works if you actually have the right number of eigenvectors. So you have to have n linearly independent eigenvectors. What's important is it doesn't matter the order in which you order the vectors or the values, but they have to be matched. So the first vector has to match the first eigenvalue. The second vector has to match the second eigenvalue. Okay, so there we go. So that's how the diagonalization works. We'll talk a little bit about why it works later, but for right now, let's move forward and just kind of talk about how we might use this for a specific problem. So let's look at this problem that we have right here. 21, 40, negative 12, and 23. And let's just ask ourselves, can we diagonalize this matrix? And in order to diagonalize it, all we really have to do is find the eigenvalues and eigenvectors, and then once we've done that, we have the diagonalized version of the matrix. Well, okay, so to find the eigenvalues, we did this last time, and so to find eigenvalues, we just take that number, a minus lambda I, and we take the determinant of it, and we set that equal to 0. So we just need to take the determinant of negative 21 minus lambda, 40, negative 12 minus lambda, and 23. And so we take that matrix, 23 minus lambda, and take that determinant. And it ends up being negative 21 minus lambda times 23 minus lambda minus, I'm going crazy. I'm getting my lambdas in the wrong place. Minus, actually plus what you get when you take 12 times 40, and that ends up being 480. Okay, and I'm already a little bit concerned, but I think we'll be able to work this out. So let's now we have to multiply 21 and 23, and let me see. It's going to be pretty close to 22 squared, but off by maybe like 1, I think. But let's just multiply them on my calculator. 483. Let's see, what was 22 squared? 44, yeah, so it was 1 less than 22 squared. So we end up getting negative 483, and then we've got minus 23 lambda plus 21 lambda plus lambda squared plus 480. And then if we come over here and let's work this out, let's put all of our numbers. So I've got a positive lambda squared, and then I had minus 23 plus, so minus 2 lambda, and then minus 3 equals 0. This is amazing, so amazing. All these numbers cancel each other out to give me a nice, pretty equation. It's almost like I planned it. Okay, so these work out. We get lambda minus 3 lambda plus 1 equals 0, and then lambda equals 3 is one of our eigenvalues, and lambda equal to negative 1 is our other eigenvalue. So we already know that whenever we diagonalize this problem, our middle, our D matrix, is going to be 3, 0, 0, negative 1. Or we could go negative 1, 0, 0, 3. It doesn't really matter. But we already know that our diagonalized matrix will have these two numbers on the diagonal, and the other two numbers will be zeros. Okay. Well, let's come along and let's try to calculate out our. Let's come along and try to calculate out what the eigenvectors are going to be. And so let's just slide this along and keep going, and let's do each eigenvalue one at a time. And so let's do that first eigenvalue. We'll do the lambda equal 3 eigenvalue. And we do lambda equal 3. What we're doing is we're just doing a minus 3i and setting that equal a minus 3i x and setting it equal to 0 and row reducing, and that just means I've got this matrix where I subtract 3 from the diagonal. So that looks like I've got negative 24, negative 12, 40, and 20, and then I've got 0 and 0. And the good news is that row reduces pretty simply, and so that row reduces to, notice they just completely wipe out. And then I'm left with negative 24, 20, 24, 40, and then that row just becomes zeros. If I wanted, let's see, let's divide everything. What's a good number to divide it by? Looks like 4 goes into them, 8 goes into them both, so let's divide by 8. And that's going to give me the matrix negative 3, 5, 0, and 0, 0, and 0. And what does that mean? That means that negative 3 x plus 5y equals 0. And if I wanted, I could now write my solution. I have to let one of them be be my free variable. Let's let the y be the free variable. And so then x equals 3/5 y. And so we'll have 3/5 here and 1. So my eigenvector could be 3/5 and 1. Or I could make my eigenvector, and I think I'm going to do this. I could choose to make my eigenvector 3 and 5. So I could make it positive 3 and positive 5. And that works out. Let's see, oh, wait, I've got that backwards. Sorry, glad you all caught it. So that, because I heard you saying that that should be 5/3, and I divided them on the wrong order. So I could use 5 and 3 here instead if I like. So I could use either eigenvector if I wanted, and we'll talk in a little bit about the different ways we create the diagonalization and how they all actually are the same diagonalization in some ways. Okay, so there's that option. There's the lambda equals 3 diagonal. Now our eigenvalue, and now we're looking at the lambda equals to 2, or lambda equal to 1. Let's see, it was -1 eigenvalue, and so that's going to give me a matrix that looks like this: -22. Right? No, -20, -12, 40, and then 24. And this is good, and then with zeros on it. And then we'll row reduce, and then notice that second row just becomes zeros. I'm getting a little tired of writing that, so maybe here pretty soon I'll just stop writing it altogether. Now what I'll do, let's divide by -20 and get ourselves 1, 2, 0, 0, 0, and 0. And so now we see x plus 2y equals 0, or importantly, x equals -2y. So this gives me our solution here. And again, we'll make y our variable. And so x equals -2y's, and y equals 1x. Let's see. Oh, wait. That should have been a -2. And so that means that one should have been positive. And wow, I'm trying to make mistakes, but I keep catching myself, which is good. Secret, I actually worked the problem out, and I have it over here on the right, and I'm checking. So no, if I were in class, I would have made these mistakes, and you would have been forced to catch me. Okay, so we see our 2 eigenvalues and our 2 eigenvectors. And so now that lets us find our diagonalization. So what is our diagonalization? So what is my diagonalization? Well, my diagonalization is what I get when I write P, D, P inverse. But my P is just made up of those 2 eigenvectors. So I could use the eigenvector 5, 3. And my second eigenvector I could use was that eigenvector 2, 1. And so I can use that for my eigenvector, 5, 3, and 2, 1. And then I can use that, and then I can use my eigenvalues in the middle, which were 3, 0, 0, -1. And then all I have to do is I have to put the inverse of that over here. So now I have to, since it's a 2 by 2, I can kind of do the inverse just by looking at it. If it were not a 2 by 2, I would have to be a little bit more careful. But we know these two switch spots, and I get a 1 and a 5. These two get negative signs, -2, -3. And then I have to divide by the determinant, which is -1. So the determinant is -1, so that means everything gets a negative. So my inverse, and again, you all are capable of figuring this out, my inverse was -1, 2, 3, -5. So this is the diagonalization of this matrix. Okay, let's just check it real quick. So how would I check this solution? To check this, I would just do, you could do it in either order. Let's do these first, and we'll do row by column and row by column. And so we'll have 5, 2, 3, 1 times row times column is -3, row times column is 6, row times column is -3, and positive 5. And we'll multiply those together. Row times column. Negative 15 minus 6 is negative 21. 30 plus 10 is 40. Negative 9 minus 3 is negative 12. 6, 12, 18 plus 5 is 23. And check, that's actually our correct matrix. And so this is a correct version of that eigenvector. Or this is a correct diagonalization. Now, it turns out there are actually other solutions. So we could have written like this. We could have written our diagonalization as 2, 1, 5, 3, and then did negative 1, 0, 0, 3, and then did the inverse of that matrix. And then we would have taken that inverse and put it right here. So actually, you could switch the order. If you switch the order of the 3 and the negative 1, you can also switch the order of those two vectors. And in fact, we could have even used a different matrix. So we could have used that 5/3 and 1 for that matrix. And then but that would have changed this inverse. So these two depend on each other, but they're always inverses of each other. So you can change which version of the eigenvector you use. You can change the order in which you write them. You just have to be consistent. Keep your eigenvalues here and make your inverse dependent upon that number. So as long as you're consistent and do everything consistently, there are multiple answers, all of which lead to the correct solution. Okay, so what I want you to do is I have that problem on there. I have problem 5.16, but we're actually going to skip it. And instead, I want you to try a different one. So I want you to try this problem. I want you to try to diagonalize the matrix negative 5, 3, negative 9, 7. So on your own, see if you can diagonalize this. And what we're going to do is I'm going to stop the tape, and then I'm going to come back in the next video and we'll solve this, and then I'll spend just a few minutes talking about why we should think this theorem actually works. All right, so good luck, try diagonalizing this problem, and we'll talk about it. And we're going to skip that 3 by 3. It's not very hard, but we're just going to skip it. All right, see you in a bit.